In order to understand the physiological processes that occur in the human body, we have to learn a little bit of chemistry. But we're going to focus primarily on the chemical structures that are relevant to the study of anatomy and physiology. So we'll be looking at things like atoms, ions, and molecules. So to begin with, remember the smallest or least complex, simplest, if you will, level of organization of the human body is the chemical structures. Those include atoms, ions, and molecules. So the human body is composed of matter. Matter is simply anything that has mass and takes up space. It's present in the human body in three forms: solids like bones, liquids such as blood, and gases like oxygen and CO2, respiratory gases. All forms of matter are composed of chemical elements, and we organize those elements in the periodic table of elements that you see here in the upper left-hand corner. Now, each of those little boxes represents a particular element, such as carbon, hydrogen, oxygen, nitrogen. There's carbon, nitrogen, oxygen, and hydrogen way over here. Now, these four elements make up about 95% of all living things. So what are elements made of? Well, elements are made of atoms. So the atom is the smallest particle that exhibits the chemical properties of an element. So basically, an atom is as small as you can get and still have whatever that element is. An atom of carbon is the smallest piece of carbon that will still be carbon, right? So atoms make up elements, but atoms themselves have what we call subatomic particles. Subatomic particles are protons and neutrons that are found in the nucleus of an atom and in orbits around the nucleus. We have the third type of structure. Those are called electrons. Now remember, protons, neutrons, and electrons are subatomic particles. Each element has atoms that have different numbers of these subatomic particles. But the one thing that is consistent with these subatomic particles, protons always have a positive charge. Electrons always have a negative charge, and neutrons are neutral. So remember, they're in here with the protons. So an atom is neutral because the number of protons that have a positive charge is equal to the number of negative charges on the electron. Okay, yes, I backed up a slide because I realized I forgot to tell you about something. So when you look at this periodic table of elements, notice that each of the elements has a chemical symbol assigned to it. We talked about carbon, nitrogen, oxygen, and hydrogen. Notice each one of them is symbolized on the table by just the first letter of the name of the element. H for hydrogen, O for oxygen. There are others such as neon, 2 letters, Ne, Al for aluminum, Ca for calcium. But then we have others that don't follow that simple tradition of naming. Some of the elements get their name from their Latin name, such as Na for sodium. Well, sodium starts with SO, but the Latin name for sodium is natrium. Same thing with K for potassium. Potassium's Latin name is kalium. So very often you will have the first 1 or 2 letters, but some of the ones that you will hear a lot about as we continue our discussion will have the Latin chemical symbol instead. Okay, now let's jump on back where we were. Alrighty, so the atomic number of an element is simply the number of protons found in the nucleus. The average atomic mass, the number of protons, plus the number of neutrons. All right, now that's just some basic terminology there. So for instance, carbon's atomic number is 6. Okay, so that means there are 6 protons, right? Because the atomic number is the number of protons. The atomic mass is the number of protons plus the number of neutrons. So how many neutrons? If the atomic number is 12, well, 12 minus 6, that means there are also 6 neutrons. Now, we've already mentioned before that the number of electrons equals the number of protons. So how many electrons? Bingo! You got it. There's 6. All right. Now, isotopes are a little bit different. So isotopes are different atoms of the same element. So elements in nature usually occur as a mixture of isotopes. Again, isotopes have the same number of protons and electrons, but differ in the number of neutrons. One isotope is usually more common than the others, such as carbon-12 that you see here. The weighted average of the atomic mass for all of the isotopes is how we get the atomic mass for those isotopes. Now, some of our isotopes are referred to as radioisotopes. They're unstable forms of isotopes because their nuclei contain an excessive number of neutrons. These isotopes have a property that's known as radioactivity, and they release radiation as they decay or break down into a more stable isotope. They also lose nuclear components in the form of high energy radiation. Those can include alpha particles, beta particles, or gamma rays as they decay or break down and become more stable. Now, some radioactivity can be harmful to living tissues. Some of it can destroy localized cancers, so we can use isotopes to target and destroy tumor cells, such as the radon from decaying uranium isotopes causes lung cancer. So some cause cancer, some can be used to target cancer. So nuclear medicine uses small amounts of radiation to provide information about what's going on in a person's body and the functioning of specific organisms, where there's activity versus where there's less. We can also look at ongoing biological processes or how much a disease has progressed and where tumors may be located. So we can use that information using medical imaging that lights up differentially based on the activity and the uptake of these isotopes and the radioactive particles by those particular tissues. Remember, electrons are found outside the nucleus, protons and neutrons are inside the nucleus. So when we draw an atom, we really don't draw the number of protons and neutrons in the nucleus, but we do need to represent the electrons because the electrons are one of the main components that determine how that chemical is going to interact or not with that atom, is going to interact or not with other atoms. So we draw electrons on rings. Now, it's important to remember they really are not located in rings like they're going around a track. They're really just in a constant orbit around the nucleus. So think of them as just moving around in all planes. So not just in a circle, but completely going all around the nucleus in an orbit. So when we draw these out, we do so based on how many electrons will be in a particular level of the orbit. So we draw the rings. So here you can look at this atom of sodium, and you see we have 3 rings. The innermost ring of all of our atoms is full when it holds 2 electrons. Now, full simply means it's holding all that it can. The second shell can hold up to 8 electrons. So let's look at sodium again. There's 1, 2. That shell is full. 1, 2, 3, 4, 5, 6, 7, 8. The second shell is full. Now, regardless what the atom is, the outermost shell is called the valence shell. The valence shell, when it's full, it's called a chemically stable and inert or inactive atom, which simply means, I don't need you, I'm not going to mess with you, I'm not going to hook up. Now, to put that in chemical terms, a complete outer valence shell gives the atom chemical stability, which means it's not going to react with other atoms. It's not going to combine. But now let's go back to this sodium again. Now, sodium has 2, 8, and there's one hanging out here. All right, so it has 11 electrons. How many protons? 11? Yeah, I knew you knew it. We just talked about that, right? So these atoms, for the most part, want to have a full valence shell. Now let's think back about this sodium again. How many in the valence shell? Just 1. Oh, wow. So this sucker's going to have 7 more electrons in order to fill that valence shell. Now, if that were to happen, that would mean sodium has met the octet rule. So the octet rule is what chemists call the atoms obtaining a full electron shell, valence shell, by either gaining, losing, or sharing electrons. So sodium only has 1 valence electron. It's going to need 7 more. Well, that's probably not going to happen. So it would be easier for sodium just to give up 1 electron than to try to steal or borrow or share 7 more to fill that shell. So sodium really likes to hook up with other atoms such as chloride. Now let's look at chloride's electron shells. There's 2. We've got 8 on ring number 2. And on the valence shell, there's only 7. So chlorine only needs 1 more electron. So it's just going to hop over here and steal this electron from sodium. Oh, now sodium has its valence shell full because there's number 2 there, full with 8. Chlorine has its valence shell full because it stole that one from sodium, and now that gives a valence shell of 8 electrons over here. Oh, well, that is going to do something really cool, and that's going to allow a chemical bond to form. Okay, now let's think back to what we learned just a few minutes ago. Remember, electrons have a negative charge and protons have a positive charge. And if the number of electrons and the number of protons is the same, then all of the positives and negatives are equal, so that atom is neutral. Okay, but now think about what we just said. Sodium gives up an electron. So if it gives up that electron, now it has more protons than electrons, so it now has more positive charges than negative charges. Okay? All right. Now what happened to chlorine? Well, your electrons are negatively charged, your protons are positively charged, and this negative charge right here on that electron now is over here on the valence shell of the chlorine. So now chlorine has 1 more positive or 1 more negative charge than the positives in the nucleus. So chlorine becomes negatively charged because it gained an electron, which is negative. Sodium becomes positively charged because it lost a negatively charged electron. That forms something called ions. So an ion is formed when an atom either gains or loses electrons. Okay? Now, positives and negatives attract. So they're going to pull together just like magnets and form something called an ionic bond. Now, if these two were just going to share electrons and one didn't steal one from the other one, we would call that a covalent bond. So we're going to see some examples of those in the next few slides. All right. The body consists mostly of chemical compounds. Well, chemical compounds are stable associations between two or more elements that combine. Ionic compounds are composed of ions held together by that positive and negative attracting each other. Molecular compounds, we'll talk about later in this chapter. Molecular compounds are formed when two or more atoms of different elements share electrons. So it's not one atom giving up and another atom taking an electron. It's sharing those electrons. An atom that has gained or lost an electron is called an ion. Cations have a positive charge, which means they lost an electron because remember, electrons have a negative charge. In addition to that, we have negatively charged ions. Oh, I don't know what I just did there, but let me get rid of that. We have negatively charged ions. My pointer's going crazy here, guys. Give me just a moment. Okay, I had to pause there for a second or two and get this back in order. All right, so cations have a positive charge because they lost an electron. Electrons are negatively charged. An anion is an atom that has gained electrons. Now, it may be one or more. Either way, remember, electrons have a negative charge. So if they gain an electron, they gain a negative charge. All right. Now, why is all that important? Well, if you look at the table over on the right side of your screen, you'll see some of the common ions found in the human body and why they're important. I mean, sodium, wow. Without sodium, we couldn't retain fluid and water balance. We couldn't maintain stable blood pressure. Our muscles wouldn't contract. Gosh, man, we could go on forever about sodium. What about calcium? Well, calcium helps to make up our bones and our teeth, helps with muscle contraction, also with blood clotting and forming the clotting factors. There's so many important ions found in the human body. So let's talk just for a moment about one of these particular ones, such as potassium. So potassium is very important in maintaining something called resting membrane potential. We'll get to that in just a minute. So ions, the important thing here to think about, ions function as electrolytes. Electrolytes are simply substances that when they're dissolved in water, they can conduct an electrical current. Electrolytes. You're going to hear more about that later. All right, so if we're going to stay healthy, we have to balance our electrolytes as part of our homeostasis. So the concentration of potassium has a homeostatic balance. Now, we lose a lot of potassium when we're sweating. So that's why we drink sports drinks that have potassium added to replace that potassium. So it helps us to be able to do the things that we need to do. But that's a good thing, right? Potassium is good. Yeah, unless you have too much. So potassium can also be extremely dangerous because we use large doses of potassium to be a part of a lethal injection when a prisoner is sentenced to death. So that injection of potassium leads to cardiac arrest and therefore death. Even though you might not have realized it, when we were talking a while ago about sodium losing electrons and chlorine gaining electrons, what happened? Well, we simply lost and gained negative charges, right? So we formed ions by losing and gaining electrons. Remember, cations lose electrons, therefore they're positively charged. Anions gain electrons, therefore they're negatively charged. And these ions then can bind together with electrostatic interactions and create something called ionic bonds. Think of it very much like the positives and negatives attract each other and hold those atoms together. The structure that's formed when a cation and an anion bind together is typically a salt. So the classic example is what we just saw previously, forming sodium chloride, which is table salt. Ionic compounds typically will dissociate or break apart in a solution, such as adding salt to water. But not all ionic bonds form salts. Some form acids and bases as well. Instead of gaining or losing electrons to form ionic bonds, some atoms reach chemical stability by sharing electrons with other atoms. The sharing of electron between two atoms forms what is known as a covalent bond, and the resulting structure of these covalently bonded atoms is called a molecule. So if two atoms share electrons and they only share one electron each, such as we have here with hydrogen. So here's an atom of hydrogen, it has one electron. Here's an atom of hydrogen, it has one electron. So rather than one stealing an electron and forming an ionic bond, these two just hold hands and play together. So at any given moment, the electrons are orbiting around these two hydrogen atoms. Now, if they share two electrons, such as oxygen, because oxygen in the valence shell has 2, 4, 6. 2, 4, 6. So each atom of oxygen needs 2 electrons. So 2 oxygen atoms come together and share 2 electrons. That is what we call a double covalent bond. And I guess you can figure out that nitrogen with a triple bond is sharing 3 electrons. All right. Or actually 3 pair of electrons. All right. The electrons that are shared with covalent bonds can be either shared equally or unequally. When they're shared equally, such as you see up here with 2 atoms of oxygen, or carbon dioxide with C2O, so CO2, with those we have equal sharing of electrons, so the charge isn't overall positive or overall negative. It's no charge, right? We have the same thing with a fatty acid, a fat called a triglyceride. So the electrons between all of these carbons and hydrogens and oxygens, they're being shared equally. Now, that creates something called a nonpolar molecule. So polar means 2 different things, right? So there's a north pole and a south pole. If you think about a battery, it's got a positive end and a negative end. That is polar. So a polar molecule results when we have unequal sharing, such as here with this water molecule. So water, remember, is H2O, so 2 molecules of hydrogen, or 2 atoms of hydrogen, 1 atom of oxygen. Now, when this sharing of electrons happens, it's unequal, and therefore it results in the oxygen pulling the electrons a little bit more, and therefore the oxygen part of the water molecule stays a little bit more negative. The hydrogens, because they're not getting to play with the electrons as much, they have more of an overall charge of a little bit positive. So that creates a negative area and a positive area, or a polar molecule. Now that's going to be very important when we start talking about properties of water. In addition to polar and nonpolar, we have something called amphipathic molecules. Amphi means both. Pathia means feeling. So an amphipathic molecule has a polar region and a nonpolar region, such as we see here with the phosphate and the fatty acid part of a phospholipid. Molecules sometimes have a weak chemical attraction to other molecules, and we call this an intermolecular attraction. One important intermolecular attraction is called a hydrogen bond, and if you notice over here, we typically delineate that with dotted or dashed lines. A hydrogen bond forms between polar molecules. It's a weak attraction between a partially positive hydrogen atom with a polar molecule and a partially negatively charged atom with a polar molecule, such as you see here with the partially positive part of a water molecule being attracted to the partially negative part of another water molecule. Well, water has some important qualities because of that. Individually, these bonds are very weak. But when you have a lot of water molecules hydrogen bonded together, then that creates a stronger bond, and it influences the behavior of water molecules and creates something called surface tension. Have you ever seen a bug crawling across the top of a puddle or a swimming pool? Well, it doesn't sink because water molecules want to stick together. Those hydrogen bonds are not being forced to break apart. So they stay together and the bugs can crawl across the water. Another thing you can do to illustrate that is if you have a glass and you're filling it with water, when it's almost full, start filling it very, very, very slowly. And you'll notice that you can actually fill the glass fuller than the glass will hold because the water will dome over the top of the glass just a little bit because of that surface tension holding those water molecules together. That's called cohesiveness.